as voltmeter. So if in some notation you see voltmeter, so that is also the unit. Both are correct, right?
Yes, sir.
And then we did some questions, right? And then we did this one as well. So now let us talk about the electric flux through a closed surface. Right. So let's talk about the electric flux through a closed surface. And before we talk about that, let us talk about the curved surface. Right. So let's say we have flux through the curved surface. Because we know that what is flux? This is simply E dot E, right? Which is EA cos theta. But if we have a curved surface, then what will happen? So you see that, let's say we have this curved surface, right? So the area vector, what is the area vector? Area vector is the line which is passing normally to the surface. So whatever which is normal to the surface. So at this area, the normal to the surface would be this one, right? At this surface, the normal to the surface would be this. At this surface, the normal to the surface is this one. At this surface, the normal. So you see that what is happening in here. So normal is always changing, right?
Yes, sir.
And also, let's say that the electric field in this region is, and we are talking specifically about the uniform electric field. So electric field is always constant, uniform. So let's say this is the electric field that we have. Parallel. All are parallel.
Okay, sir.
So all these are parallel, right? So this is the electric field. They are uniform. Now you see that for this one, this is the angle theta. 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 So what is happening? Theta is always changing in this surface. Right. If I take this area, then this is the normal. If I take this area, then this is the normal. So this theta is always changing. Then I cannot calculate the flux using this one form because this theta is always changing, right?
Yes, sir.
So what I will do is that I will take a very small area which is whose normal is always parallel to the electric field. So what I will do is that I will take, so to get rid of this problem, we will assume a very small area, let's say ds, which is always in the direction of electric field. So what we'll do, we'll take a small area ds in here, 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 small area ds in here. And this one is always in this direction. This one is always in this direction. Small area ds, this is always in this direction. Small area, this is always in this direction. So this is this electric field is parallel to the surface surface area ds, right? So your theta would become how much? What would be theta? This is always parallel, so theta is always 0 degree, right? So you will take this small angle E dot ds and you integrate through whole area, right? And this is how much? So this is EDS cos theta, and this is 0, so this would be simply E dot EDS. And then you just integrate this whole area. So you just integrate all this area, so you will get the flux. Is it clear to you? Is it clear? Yes, you got disconnected. So yeah, can you hear me?
Yes, I can hear.
Yeah. So we have this thing, right? And yeah. So what do we do is that we take this small area and then we integrate over all this area. So this E is uniform. It comes out of the integral, and you only have to integrate this, right? So this is your area. Is it clear?
Yes, sir.
Okay. So now let us. Yeah. So we have understood this thing. Let us apply for a spherical charge distribution, right? So let us apply this for a charge, and then we will take a sphere which is uniform, right? So let's apply this
Okay.
for a unit charge. Flux through the sphere. So let us see what happens. So we have a small charge q, and you will see that for small charge q, the electric field lines pass like this, right? So they go outwards in this direction. In every
Yeah.
direction, they go like this, right? So
Yes, sir.
what we will do is that we will take a spherical charge distribution, a sphere, and let's see through this sphere what is the flux. So again, what we will do, we'll take, you see that the electric field is passing like this one. This is the electric field. I will take a small area ds, right? And its normal would be in the same direction. I will again take the small area ds, and its normal is again in the same direction. So this is ds, and this is the electric field. This is the electric field, this is the electric field, right? And this is the
Yes.
ds. So both are, theta is how much? 0 degree. Clear? So what
Okay,
would
sir.
be the flux? What would be the flux? Flux would be integral And now what kind of integral is this? So this sphere is an open surface or closed surface. What kind of surface is this one?
Close.
Closed surface, absolute. So whenever we have closed surface, so we denote it like this. This is the closed surface, right? So this is the closed surface. In integral, so in integral, we just draw this circle. So this is the closed surface and E dot ds. This is the flux, right? Electric field is a vector quantity, area vector is a vector quantity. So now we already know that this is E ds cos theta. And we have taken our theta in such a way, our ds in such a way that this is 0. So cos 0 is 1, right? So this is simply E ds. And you see that this electric field is uniform. So this would be, I can take it outside. And this is integral of this ds. So I have to integrate this whole area. Can you tell me what would be this area? What would be this whole area?
Um,
What kind of shape is this?
it's a circle.
This is sphere, sphere. We are talking about circle is not a closed surface, right? Circle is open surface.
Yes, sir.
So this is a sphere, right?
Yes, sir.
So if I integrate this whole sphere, then what I will get? The surface area of the sphere. Right, let's say that this is R. Okay.
Yes.
Now, can you tell me that what is the electric field of this charge at this point, at the surface of the sphere? What is the electric field of the point charge? What is the electric field of the point charge? Electric field of point charge. This we have done in the electric field topic. So you have this Q charge, you are calculating the electric field at R distance. So what would be this electric field?
Um,
KQ by R. This was the electric field, right?
yes, sir.
So this electric field is K, and we have assumed Q by R square. And then 4 pi R square. So this K is how much? What is this K?
See.
K is 1 by 4 pi epsilon 1, right?
Yes, sir.
And then we have Q, we have R square, and then we have 4 pi R square. So R square cancels, 4 pi cancels, and we have Q by epsilon naught. This is what? Flux. So this is how you get your Gauss, right? This is how
Yes,
you
sir.
get your Gauss law. So please note down this thing, and then we'll talk about the Gauss law. Please note it down.
Okay, sir.
And whenever you want me to scroll down the screen, please tell.
Okay, sir.
Yeah, whenever you want me to scroll down the screen, please tell me. Yes, Thameem, your internet is not working properly, right?
It's actually working fine, sir, but my tab, I think it's a bit slow or something. There's only
Oh,
issue on my tab, right? Yes, sir.
oh, so it's only happening in your tab. Maybe you have
Yes,
to
sir.
remove some junk files, right? You have to clean your
Yes,
tab.
sir. Yes, sir.
Yeah, so please note this thing down, and whenever you have you want me to scroll down the screen, please tell me.
Okay, sir.
Yes, do you note it down?
No, sir, I'm still not. You can scroll down. Done.
Done. Okay, so
So,
now
sir,
let
but can
us,
you explain
yes,
this once? I didn't quite understand this properly.
which way? So you want me to explain this thing again?
Yes, sir.
Good. So yeah. Okay. Good. Good. So whenever you have any doubt, please don't hesitate. So you see that we know that this sphere is what kind of sphere? So how should I show this? So yeah. So this sphere is the closed one, and this is the curved one, right? This is not the plane
Yes, sir.
surface. So we have a curved surface, and then we cannot apply again that idea. EA we cannot apply, right? Because every
Yes, sir.
time this theta is changing. So we take a very small area element ds, and then we integrate through the whole area. So we just sum up all those ds, right? So that is the
Yes,
thing
sir.
that we are showing, and this is the flux. Flux is simply E dot A. So we sum up EA cos theta 1 plus EA cos theta 2 and sum of them up. So this is what we call the integration of EA cos theta. This is what we are doing. But we have taken this area in such a way that this theta becomes 0. So this theta is 0 and we have simply E dx. We also know that electric field, and this symbol is representing that we have a closed sphere, not the open surface, but the closed surface. So if we integrate this thing EDS, and because this is a constant. So whenever you have a constant in integration, then you take this thing outside of the integration, right?
Yes, sir.
And now you have to integrate simply dx. Dx is sum of all those things, right? That is the summation of all those things. So if we sum up all this area, these are small patches. So this will make a whole sphere, right?
Yes, sir.
And what is that whole sphere area? That is 4 pi r square, right?
Yes, sir.
And now because this is the point charge. So for point charge, what is the electric field? At this point, at this point, at this point, what is the electric field for the point charge? This is simply kq by r square. We put that value and we solve this thing. So then we get the flux as q by epsilon. Is it clear?
Yes, sir.
Okay, so this is what we call the flux. This is what we call the Gauss. So what is the Gauss law? It states that the flux inside or the flux through a closed surface is equal to 1 by epsilon naught times the charge enclosed by the surface. Right, so this is what we call that flux, which is E dot ds. This is equal to Q enclosed by epsilon. So this is what we call the Gauss. Is it clear? Is it clear? Yes, Thameem, can you hear me? Yeah, I guess again your iPad is. Uh, hello, Thameem, can you hear me? Yes, yes, Thameem, can you hear me?
Oh, yes, sir.
Yeah, so this is what we call the Gauss law, right? And it has a wide application. Those applications we will see. So the flux through a closed surface. So the surface should be closed. That is the idea. The surface should be closed, right? So
Yes,
that
sir.
is the important thing. And it is equal to 1 by epsilon naught times the charge enclosed by that surface. So that is the Gauss, right? And
Yes, sir.
yeah, so the important thing to note in here that the Gauss law or the Gauss law or the flux inside or the flux through the surface is not dependent on the shape of the surface. right? So whatever kind of surface you take, and let's say if this is Q charge, you take this Q charge. Let's say you take this Q charge. So whatever surface or whatever shape, whatever closed surface, right? Whatever closed surface you take, this flux would always be what? This would be Q enclosed by epsilon for all the cases, right? For all the cases, this
Yes.
would be enclosed by. So no matter what is the shape, what kind of closed surface you are taking, the flux would always be the same, right? Or the Gauss law would always be the same. So that is the idea. And again, we have, and the second thing is that the flux through the closed surface due to dipole is 0. Why this is 0? Let's say we have this surface and then we have a dipole. So what is a dipole? Minus Q and plus Q. So if we calculate phi, so this is Q enclosed by epsilon naught. Q enclosed would be how much? Q minus Q. So Q minus Q is 0, so this would be 0. Right?
Yes, sir.
This is the second point. And the third point is that the flux through the closed surface is only dependent on the charge inside the surface. Right. It is not dependent upon the charge which is outside the surface. So it is only dependent upon the charge which is inside the surface. Right. So these are the
Yes.
important things to remember. And then we'll see what are the application of this Gauss law. So please note down these things, and then we'll talk about the application of Gauss law.
Yes.
Yeah, quickly note this thing down, then we'll talk about, we will use this idea to calculate the flux for different kinds of shapes, right?
Yes, sir.
So this
Done, sir.
done. Yeah, always remember that this should be closed surface. So the surface should be closed, right? Then only this would be Q enclosed by epsilon. So the surface should always be closed, right? And it is sometimes denoted as this thing. So it is sometimes denoted as S. S represents the surface, right? So you can write you can simply remove this thing or you can write this thing. So both are correct. Right? You can write
Okay.
you can either write this thing or with this S. Both are correct. So now let us use this thing to calculate the flux through some surfaces. And then we'll understand the application of this thing. So let's say I want to calculate the flux passing through, let's say, the hemisphere. So we have a hemisphere, and at this point, some Q charge is there. And I want to calculate what is the flux passing through this thing. What is the flux through this surface, through this hemisphere? What is the flux? Right.
Yes, sir.
So what I will do is that I will make. So we have this shape. I will make an arbitrary full sphere. Right. So this is a hemisphere, and I will make an arbitrary full sphere, and this charge is inside. So for this whole thing, can you tell me what is the flux?
Mm.
This is a closed surface, right? A closed
Yes.
surface. So the flux would be simply Q by epsilon naught, right?
Yes, sir.
And this is made up of two hemispheres, right? Two
Yes, sir.
hemispheres. So this is Q by epsilon naught. So this would be phi 1 would be Q by 2 epsilon. So hemisphere would be simply Q by 2 epsilon. Is it clear?
Yes, sir.
So this is one such question. Another question that they may ask is this one. So you have a sheet, right? And on top of this sheet, let's say at a distance, some charge is put. So let's say some charge is here at a distance. Now, what is the flux passing through this sheet? What is the flux passing through the sheet? So how can we calculate this thing? So again, the idea is to make a closed sphere. So for a
Yes, sir.
sheet, this is a square sheet, right? This is A, this is A. This is also A. So this is a square sheet, right? And yeah, so let me, this has not the side A, but whatever, the side could be different. But this is a square sheet. So if I want to make a square sheet a closed surface, then what will I have to make? What will be the closed surface of this sheet if I want to make this thing a closed surface?
Yes.
So let's say you have a box and right, let's say one side of the box is open. So consider that open side as your sheet, and then you want to close that sheet. So you will make that thing a cube, right?
Yes, sir.
So this is your sheet, right? Let me make this thing like this. So this is the sheet, right?
Yes, sir.
This one is the sheet, right? And then I cover this sheet with the 5 other sides. So this becomes a cube. This is the sheet that I have. And on top of this sheet, I have this Q charge at a distance. Right, this is the diagram. Clear?
Yes, sir.
So now let's say that this is, yeah, I will write that thing later. But this has become a closed surface. So then what would be the flux through this closed surface? Yes, what would be the flux through this closed surface? Whenever you have a closed surface, then for every closed surface, the Gauss law says that flux would be what?
It's
What is the Gauss law? Gauss law says that flux inside a closed surface, flux through a closed surface is 1 by E times the charge enclosed, right?
yes, sir.
So this,
EDDS.
so EDS, we are not bothered about that EDS. The flux is simply Q by epsilon, right? Because this whole
Okay.
thing is a closed one. This whole thing is a closed surface, right?
Yes, sir.
And how many surfaces are there? So we have only this surface. Let's say this is phi 1. So we have phi 2, we have phi 3, we have phi 4, we have phi 5, and then rest one. Which, what is the rest one? So this phi 6. Right? So we have 6 surfaces. So this is 6, phi 1, and this is Q by epsilon naught. So this phi 1 would be how much? This would be Q by 6 epsilon. So flux through this thing would be Q by 6 epsilon. Is it clear?
Yes, sir.
So the idea is to make a closed sphere. That is the only idea that we have to think about. Right. So yeah, you just note down these 2 questions and then we will understand. Note down these 2 questions and then we'll understand the application of Gauss. Please note it down.
Yes, sir.
Yeah, so we will have an assessment on the electric flux. So please take that and yeah, whenever you have noted down this part, please tell me. Is this thing clear to you?
Yes, sir.
Okay, then yeah, please note it down. Yeah, whenever you have noted, please tell.
Okay. Done, sir.
Okay. So now let us understand the application of Gauss. And to understand the application of Gauss law, firstly, we require the Gaussian surface, right? So what is a Gaussian surface? Right, so this is a very useful tool, hypothetical tool to simplify the closed surface integral, that is what? Which is that is your E dot ds. So this surface is what we call, this is surface what we call the Gaussian surface, right? So in different
Yes.
cases, we have to take different Gaussian surface. And what is the criteria that we apply to choose this Gaussian surface? So to choose the Gaussian surface, what should we have? We must have, first thing is that E is uniform, right? So that it comes out of the integral, so that it comes out of the integral. Second point is that E should be, or the surface should be taken in such a way that E is either perpendicular or parallel to the surface. Let's say these are the two criteria that we have for a Gaussian surface, right? And
Yes.
yeah, and the third thing that it is a closed in the surface, so that thing is there. But this is very important. E should be perpendicular or parallel to the surface. Right, so how this simplifies the answer, we'll see in the application. So we can have different kinds of Gaussian surface for different kind of charge distribution. Right, so for different kinds of charge distribution, we can have different Gaussian surfaces. So this is dependent upon the charge distribution, right? So let us understand the charge distribution.
Yes.
So when we have continuous charge distribution, then it can be of three types. What is the first type? That the charge is distributed along a line. So along a line, and that is what we call a linear charge distribution. So what is that? So let's say this is the charge that you have. So along the line, you have this charge, right? So this is what we call a linear charge distribution. And for this linear charge distribution, we have linear charge density. And what is that? So let's say the whole charge is Q and this length is L. So this linear charge density, which is lambda, this is represented as Q by L. So this is the linear charge density. Give me one moment. You please note down these portions. So please note down this Gaussian surface. And yeah, I'll be back in a minute. So give me one.
Okay. Okay.
Yeah, so okay, you please note it down and I will write simultaneously because this is not right. I will write simultaneously. So you just note this thing down. And then
Okay.
we have along the surface. So this is called surface charge distribution. For example, we have this sheet, and along this sheet we have this charge. So for this thing, we have surface charge density. And this is represented as sigma. And this is, let's say the whole charge is Q and the area is A. So area is A. So this is Q by A. And then finally, we have along the volume. So this is volume charge distribution. And what is the example of volume charge distribution? So let's say this one. Across the volume, we have this thing. And in this case, we have volume charge density. This is represented as rho, which is Q by Y. So these are the different kinds of, please note it down. And whenever you have noted, please tell me.
Okay. Done, sir.
Done. Okay, so now we have to talk about application of Gauss law. Right. So there are three applications. One is to find out the electric field of infinite linear charge density or linear charge y. Right. And then
Yes,
the
sir.
second thing is that we can calculate the electric field of infinite sheet. Right. And then the third one that we can calculate is the electric field of hollow non-conducting or hollow conducting or hollow or this is solid conducting sphere. So all these things are same. This one, this one, this one. All these things are same. So we have to use the Gauss law to find out the electric field of these quantities, right? So these are the things that we have to calculate. And let us understand the first one. So we have the electric field of infinite linear charged wire, right? So we have this wire which has infinite charge distribution, right? And its charge is, let's say, Q. So what we will do is that, let's say that from here to here, the charge is Q and the length is L. So let's, what we will do is that we will assume a Gaussian surface like this. So this is the Gaussian surface.
Okay.
Right. And its charge distribution, its charge density is linear, which is lambda. So its charge density is lambda. And from here to here, this length is, let's say, L. So this length is L. Okay. And let's say that this is R. This is R distance. So we have taken this Gaussian sphere, and we know that for this thing, how the electric field goes. So the electric field goes like this one, right? The electric field goes like this one. And you see that for this thing, right? So this is the electric field. So you see that for this cylinder, how many surfaces are there? How many surfaces are there? For this cylinder, how many surfaces are there? Yes.
So is it one?
One. Okay, so let's say you have a glass. So a glass has, and let's say that it is, the glass is closed. Or let's say you have a Pepsi can. So Pepsi can has top surface, bottom surface, and then curved surface. So it has three surfaces, right?
Yes, sir.
So
Okay.
this is, let's say, one surface. This is second surface, and then this one is the third surface. Clear? So
Yes, sir.
phi would be phi1 plus phi2 plus phi3. And this is what? This is Q enclosed by epsilon naught. So this is this thing, and we know that this is enclosed E dot ds, right? And then this is
Yes.
Q enclosed by epsilon naught. So let's not write this thing. Let's first write this thing. So this is E dot ds. Now you will see the importance of this Gaussian surface, right? So this E dot ds is, it has three parts, right? One is E dot ds, right? And let's say this is phi1, and the other one is E dot ds 2, and then the third one is E dot ds 3. So there are three contributions. We have changed this closed integral in three surfaces, right? Is it clear?
Yes, sir.
Okay. And now this would be EDS cos theta. One, this is EDS cos theta 2, and then this is 3, EDS cos theta. Now, if we look at the first surface, so this is the first surface, right? This is the first surface, and the electric or the area vector would be in which direction? For this surface, the area would be normal to this surface.
Yes, sir.
So the angle between the area vector and the electric field, how much is theta? How much is theta? This is normal to the surface. This is electric field. So what is theta?
90.
90 degrees, right? So this is 90 degrees. Similarly for 2, what is theta? The area vector is this one.
Yes, sir.
So again, theta is 90 degree, right? For
Yes, sir.
third one, theta is 0 degree, because the area vector is along the same direction. Area vector is along the same direction, right? For the curved surface part. So now you see the importance of this surface, this cylindrical surface. So either we have theta, which is 90, or we have 0. So that is the use of this Gaussian surface. That is why these are very important. So this one is cos 90. So this is 0 because theta is 90. This is 0 because theta is 90. And then we have only the third one, which is EDS. And then how much is Q enclosed? Q enclosed, we know that lambda is charge density. So this is Q by L. So this Q enclosed is simply lambda into L. This is Q enclosed. So this is lambda into L divided by epsilon 1. And then what is this thing? So EDS, this E is taken outside, and then this is DS. And this is pi lambda L by epsilon 1. Can you tell me, this ds is the curved surface. This is the third one. So what is the curved surface area of the cylinder? What is the curved surface area of the cylinder? If you have the cylinder, what is the curved surface area? This height is h. This is r. So what is the curved surface area? Curved surface area is 2 pi RH. Right? This is the curved surface area of the cylinder. Right? Is it clear?
Yes, sir.
So in our case, this would be simply 2 pi r and L. And this is lambda L by epsilon naught. L will cancel. And electric field would be lambda by 2 pi r epsilon. So this is the electric field, and if we write it in proper manner, so this is lambda by 2 pi epsilon naught r. So this is the electric field of a linear charge wire. Is it clear to you?
Yes, sir.
And any doubt in these things? Any doubt that you have?
No doubts.
Okay, then please note it down, and then we'll understand about the other surfaces. So then we'll talk about the surface charge density sheet. Yeah, whenever you have completed, please tell me.
Okay.
Yeah, whenever you have a please tell me.
Okay, sir. Almost done. Sir.